This time we want to talk about 1.6, the equilibria and phase line. We will focus only on autonomous ODE. Okay, that means the ODEs that has only a y involved in your derivative. So if something like this happen, it's not autonomous. And if something like this happen, like the logistic, it is autonomous. Okay, like we said, these are the ones which only generate on themselves. They do not need inputs from the environment as time goes by. It's always look at yourself, and then you know what you're going to change next. All right, the first concept we want to talk about is going to be phase line. This is a very handy tool for you to do qualitative analysis. Not so accurate, but it will tell you the trend, the end, and some other useful information really quickly. Okay. So what we have here is going to be something like this. Let's take an example of this. Note, this is autonomous. Therefore, I can draw the slope field at 0, 1, so it's going to be like that. But once I know it's like that, because it's autonomous, that means t really doesn't change a thing. So as long as I have the same y, I will have the same thing for all the t for this y. Similarly, for this one, I will have the same thing horizontally. Okay. So with all these kind of redundant vectors you need to draw, it starts to hit you. That is like, can I squeeze all the information and just, write down some simplified version of this, which means I can actually compress everything of this two-dimensional ty plane onto a single line. Okay. Moreover, and I can only draw, then I only need to draw this vector for once. Even though I didn't draw it, you will know, okay, if you want to expand the whole thing, it's going to be just repeat this one for a lot of times. That's the first good news, okay, which is great. The second good news is, what if I don't care too much about how fast you are growing? That means how fast you are growing or decaying, and I only care about how fast, if you are growing or decaying, but not how fast. Then all you need is, you just need to know it's pointing up or down. You basically don't need to know, okay, the difference between pointing up very slow, pointing up really quick. You want to squeeze them all to be just pointing up. Then not only you can draw the whole vector here, you can actually change them. You can change them to be only giving you the information of increasing or decreasing. Okay, so let me say this. For autonomous, what's going on here? I cannot go back. That's too bad. Okay, let me then do this. For autonomous, all we care about is, the vector field at y. Therefore, we don't need a t function. We just need a t-axis. We just need a y-axis. Okay. Second, we do not care about increasing fast or slow. We just care about, are you increasing or are you decreasing? But not how fast. Moreover, we care about, are you not increasing or decreasing, which means you are not changing. Then we can squeeze all the information into one single line involving only y. And we call this one the phase line. Okay. Now all we need to do is just put on this phase line where the function is increasing, where the function is decreasing, and where the function is not changing. But now ask yourself, how do you find that? Well, it's very easy. What do you mean by increasing or decreasing? Increasing means y prime is bigger than 0. Decreasing means y prime is less than 0. Okay, and not changing, which is actually the equilibrium we will call where the y prime equals 0. And what is your y prime? Well, your y prime is nothing but your differential equation, which is given by fty, but no t, so it's just y. So is y prime bigger or less or equal to 0 really depends on what your y value is. With this, you can actually draw the phase line to tell people on which part is increasing, decreasing, or 0. Okay, let's see some examples. The first one is y prime equals 0.1y. Okay, how do you know it's increasing or decreasing or not changing? Well, I set y prime equals 0. That implies 0.1y equals 0. That implies y equals 0. So at this part, my y is not changing. So I just put a pointer here. There's no vector. No pointing up, no pointing down. Okay. Now what about above this y? That means when y is positive, clearly everything is going up. What about below this one? Everything is going down. What about here and here? Well, if it goes up, all goes up until you reach another part where my derivative equals 0. Since there's no other point where I have equilibrium, this one is up, then everything above is going to be going up. Okay? So that's my phase line for this differential equation. What information does it give you? Well, it gives you a lot of information. By looking at that one, you will know several things. Number one, you will have a solution starting from this dot and it never changes. Okay. From here, you also know if your initial value is above that, you will just go up and never ends. If it's below that, you know your solution is going to go below and never ends. The only information you're missing is actually you don't know it's going up like this or actually slowly. You don't know that because you don't have information about t. But it's still not too bad because you know the rough trend by just looking at this one phase line. Okay. This also tells you how to actually draw the phase line. That is, set your derivative to be 0 to find where the derivative can possibly change sign from positive to negative or negative to positive. Then this point naturally divides your whole value into several intervals. And on each interval, you only take one possible sign. Okay, it's either positive all the time or it's either negative all the time. And you can only change the sign when you hit where your derivative equals 0. Okay. Similarly, let's draw this one, which is logistic, which we know what the graph looks like. But now just do the phase line. So what do? Number one, you take your y prime equals y, 1 minus y equals 0. That gives you 0 as a special equilibrium, which is not changing, and 1. Then naturally you have 3 parts. Okay, above 1, between 0 and 1, and below 0. Now for each one, you just simply verify is it positive or negative. This is something we have done in calculus constantly. You can either do it by argument, or you can just simply take a test point. For example, take a 2, take a 1/2, take a negative 1/2. Okay, you will be able to find it's gonna be negative, therefore going down, positive, therefore going up, and negative, therefore going down for the phase line. Okay, if you really think about it, it's actually not hard to see. Okay, what you're doing is nothing but, you know, if you flip this one for 90 degrees, you just have a y, you have 0, you have a 1, and this one is nothing but a quadratic, which looks like this. That's what we know about the graph of y, 1 minus y, right? So of course it's negative here, positive here, negative here. Okay, so it's negative here, positive here, and negative here. And then of course you just need to know what positive and negative means in terms of phase line. Okay, but once you have that phase line, what does it tell you? It tells you the whole thing is going to be this. If you start from any initial value between 0 and 1, you go up but never touches. Remember we said they cannot intersect each other if it's unique. If it goes above, you always go down and come to here. You don't know how fast though, but you do go down and come here. And if you are even below, which is not possible in real life because we have an initial population which is negative, but mathematically it makes sense. This one is going to go to negative infinity. That gives you the rough qualitative analysis of what's going on with the solution of a certain differential equations in a very, very quick manner. So that's pretty nice. All right. Remember the free dive? We took a lot of time to do a separable thing, and we try to analyze what's going on. We have numerical method, but if you think about it, it's nothing but this. Actually, mg equals g minus kv squared. But let's just take mgk to be 1 to make it simpler. Not 0. To be 1. Okay. Then we just have v prime equals 1 minus v squared. And can you draw the phase line? All right. Now, kind of in between, you can do it yourself. Negative, positive, negative, therefore goes down. Negative, positive, negative, therefore goes down, goes up, goes down. With that in mind, automatically you know. This is 0, this is 1, this is negative 1. This is one solution, this is another solution, which is not so interesting. But anything in between, if you start from here, it goes up. If you start from here, it goes down. If you start from here, it goes down. So it's very similar to what you just got for logistics. So no surprising, like if you start with a certain kind of velocity, okay, eventually you will have the final velocity to be approaching this equilibrium here. All right. One interesting thought experiment is to think about why we have this. That basically means your whole person is actually floating in the sky. Okay, you literally just float to the sky. Okay, you go up. Think about what's happening there. Okay. All right. That's the idea of phase line. From here you can see it's pretty neat. Several things we wanted to point out, just some special cases. Okay, so things to look for. Tips. Some special cases. The first one is something like this. Let me make sure. It's 1 plus y squared. Okay. It is not hard to do the equilibriums and the phase line. Here is negative 1. Below negative 1 is like that. Above negative 1 is like that. All right. So how do you interpret this? Let's just do this. We don't have to draw the 0 axis every time. You basically have, if you start from here, or if you start from here, something's, yes, okay. And if you start from here, you go to here. So it seems like the whole thing goes to infinity, right, forever. But now if you solve it, I will skip it. You will have 1 y equals negative 1 minus 1 over t plus c. So what you will have is, you will not have this solution. I will draw it here. Okay. But instead you will have this solution. Okay, which means you have a vertical asymptote and you could never cross it. From here you can see the phase line does not tell you anything about the t direction. Therefore, if this one goes up, it's very easy for you to think about maybe this one goes to infinity as time goes to infinity. But the problem here is actually sometimes you go to infinity with infinite time. And phase line cannot tell you the difference. So be careful when you do draw things like this. Don't always just go say, hey, this one goes to infinity as t goes to infinity. Maybe it goes to infinity with infinite time already. And that is where the c is. Okay? Second, possible situations. Well, I think for now you probably start to see why we are doing this. We're doing this because first we want to identify where the whole thing is 0. Then at a different side of 0, you will only have one sign. It's either positive or negative until you hit the next 0. Otherwise, this what's positive will stay positive. You cannot change your sign unless you hit it, right? Okay. But then your question becomes, is that really so? Is that the only possibility that your derivative can change sign? It's almost like a question back in Calculus 1, right? Can your derivative change sign? Well, one possibility is f prime equals 0. Then automatically you know that another possibility, that is f prime y equals does not exist. So even so far, we have done a lot of things, okay? Every time what we do is we start with setting y prime equals 0, which is f y equals 0, to solve for y, to find all the points where you have 0, and then we do plus, minus, plus. But actually there is another possibility which we never talk about. That is, this should also be included. Okay? You can try a very easy example. Y prime equals 1 over 1 minus y. Okay? With that in mind, you can easily see, even though this one never equals 0, but your derivative does change sign at 1. Above 1 is negative, below 1 is positive, so the whole thing goes like that. The only problem is, I would suggest you don't do a dot here, because dot usually means there is a point. That means the value is possible. What you should do is, you should change this one to a circle to indicate, not including this one. That is 1. So above is below, and this is that. And if you go ahead and draw it, just be careful you don't have equilibrium solutions here, even though your function changes sign. Okay. That also means what? That also means when you draw the solution, before what you did is, you would definitely have a solution looking like this, and a solution looking like this. Okay. Okay. But now you just don't have this equilibrium solutions in the middle. All right. That's what we have. Some side topics. Now the second thing, of course, we want to talk about those kind of equilibriums. We call them equilibria. And we figured we have 3 possible type of equilibrias. The thing like that. Actually, let's skip this arrow. We know pointing up is this one or this one. Okay, these are the 3 possible situations which can happen at those kind of zeros. Okay, and I mean, what's so special about them? Well, this one you can see. At here, things don't change. But if things are a little bit away from here, things got pulled. Things got attracted back to where this is. So we call this a sink. Or we can say it's like an attractor. Okay. This one, if you stay here, you stay here. If you're a little bit away, you actually move away from this equilibrium forever. This is going to be called a source. Like something projecting all the way to all kinds of directions. Of course, the third one is going to be called a node. Okay, so we have 3 types of special points like that. Now we want to classify them. Okay, and that's what we have for equilibriums. So the first one, equilibria, or let's call equilibrium solutions, are the places where such that ft, y, in our case fy, and we already know why they are important. Because they are very special solutions. Okay, if we take y, 1 minus y, we can easily see the equilibria is going to be y equals 0 and y equals 1 are equilibrium solutions. They are very special. Okay. Now second, we have the definition of the three type. I will just put it there. Equilibrium types. We have a sink, something that attracts the initial values around them. We have the source, something that repels the things that are around them. Stop doing that. And finally, we have the node. All right. So we have these three types corresponding to, for sink, if you start here, you stay constant. If you don't start here, you got attracted to the constant. For source, you start from here, you're a constant. If you're a little bit away, you move away from the constant. Okay. Finally, it's a node. It's hard to say. Are you attracted or are you leaving? It really depends on which side are you on my equilibria. Now, very easy things for us to see is for y prime equals 0.1 y, equilibrium solution, y equals 0. What happens to it? It's a source. Y prime equals y, 1 minus y, the logistic. Okay. Equilibrium solutions are y equals 0, y equals 1. Okay. Draw the phase line. Okay. This one is going to be a source. This one is going to be a sink. Okay. Y prime equals 1 plus y square. Y equals -1. Certainly this is a node. So that's how we tell. Okay. When you go to 2 dimensions, things become even more interesting. But for now, I think it's pretty easy to understand. Of course, we have another quicker way to do this. Maybe quicker. Okay. So I will just write down. It's called linearization. Hold on. What I am here? Equilibrium times. Okay. Linearization theorem. Suppose we already have equilibrium. Then what we can do is we can check the derivative of f with respect to y at 0. Okay. And we may have 3 possibilities. Okay. If this is less than 0, bigger than 0, and if it is 0, indeterminate. It can be a node, but it can also possibly to be a sink. We really don't know. Okay, so for example, next time what we can do is we can take y prime equals y times 1 minus y. We know y equals 0 and y equals 1. We want to know, is this a sink or source? So type. One way to do it is actually draw the whole line and try to do all these and try to get it. But another way to do it is simply just take this one, okay, and take the derivative. And then plug in 1. Less than 0, therefore sink. So we don't have to actually draw the phase line. Sometimes the phase line may be difficult to draw, but computing the derivative may be easy. And what about 0? You just plug in 0 into this. Then automatically you know, okay, it's positive, therefore it's a source. So this is actually a really nice way for the computer to do this stuff. If you calculate the derivative, then you have multiple points, you just plug them in. Depending on it's positive or negative, you have sink and source automatically output it for you. And that's basically one trick you can do. Why is it this case? Let's just take one example. You already know it's equilibrium. Our question is why this one corresponding to a sink? Okay, and you know what sink looks like. This has to be the case. That means you have to have this case. Now remember, this is the positive direction, so basically you're trying to say is, well, this is your y-axis. This is where your y0 is. You want this to be negative. You want this to be positive before. So what about the derivative here? It has to be positive. It has to be negative. You went from positive to negative, your value decreased after 0. Therefore, you have a sink. Okay. Similarly, you can draw the source. You want positive, negative. Positive, negative. Therefore, your derivative has to be positive. So that's a very simple way to analyze the whole thing. Of course, what you were doing is linearization, because locally, you replace this one by a straight line, which is, the first derivative as a slope. All right. Finally, one application, just to show you why this is useful. Let's talk about something called Modified Logistic. Okay, we have the logistic. Now I have the complete version. Or let's start exponential to put them together. Exponential growth. The only feature we have is your growth number is proportional to your current number. So that's great. After that, you added something. Okay, that is, you have the maximum capacity. It makes sense because in real life we do not have unlimited resource. Your environment cannot sustain what's going on. All right. Now from there we want to add one more thing. That is, we want to have the minimum sparsity. This works especially well for races that collaborate with each other. So let's say if you throw 3 people into a wild environment, maybe they will just die very quickly because they do not have sufficient enough number to survive. So if the species need a sufficient amount of number of population to start with, otherwise they die out. This is called minimum sparsity, which is called M. Then you can modify the differential equation to be this. You still cannot and has to be adjusted for the limit, but also you add one more term, that is y over m minus 1. So this new additional term does one thing. That is, if y is bigger than m, the whole thing is positive, survive, or in our way, grow. If y is less than m, your derivative is less than 0, you decay. So that means you won't be able to grow or reproduce or survive until you have a sufficient amount, which is m. Below that, you just simply die out. Okay, that's modified. Can you solve it? Technically, it is separable, so you can. Of course, we don't want to do it. But really, just analyze it. You will find, well, this is a thing. This is an equilibrium. And this is an equilibrium. Usually m is below n. Okay? Otherwise, the whole thing does not even work. Okay, can you do the analysis? Okay, when things are very small, you have negative, positive, negative, together, positive. Okay. Now you go from here to here, you change the sign, you change the sign, you change the sign. Now with that in mind, hold on. Ah, yes, okay. With that in mind, we can have okay. Now what that gives us is going to be the one on the bottom doesn't make sense at all. Okay, you start with initially a negative population, so we ignore that. But what this one tells you is n is going to be a attractor. That means as long as you start to grow or decay, eventually you will end up at n. The sparsity m is going to be a source. That means, okay, if you're above the m, to n. If you're below m, you go to 0. That actually matches what we expected. That is, if you don't hit the sufficient amount of your population, you die out to 0. But if you hit it, once you go past it, you will go to another equilibrium. You will not stay at m unless you start exactly with m. Okay, that means you're barely surviving. All right. That will be everything we need for equilibriums.